혹시 보이시나요?
네, 잘 보입니다.
네, 그럼 바로 시작하겠습니다.
네.
Hello, today I'm going to introduce our project result called pneumonia classification in chest X-ray images using uncertainty modeling. Our team members are Kyungmin-jo, Chang-hun Park, Wan-hee Kim, and Min-gyu Kim. And this is the content of our presentation. So first I'm going to introduce what is pneumonia classification and why it's important and why it's difficult. And I'm going to share some previous works, and after that we are going to point out what is the problem of the previous models and what's our solution and experimental result and conclusion. So first, pneumonia is in Korean, 폐렴 is one of the most serious disease worldwide. So according to the previous papers, they point out about 50,000 of people die from the pneumonia every year in US alone, and the other paper says in worldwide, 4 million people dies yearly. And as we all know, nowadays COVID-19 is breakout, and it is one of the pneumonia. So I think it's more important nowadays. And the figure 1 in here shows the how what's the difference between lung with pneumonia and the healthy lung. So as we can see, there's some inflammation area in here, so we can easily recognize if this lung is with disease or it's healthy. But the problem is the real world is not like this figure. So in real world, we only use the chest X-ray chest X-ray image, and it's the easiest and the best way to diagnose if this patient has pneumonia or not. But there are two problems. So first, in the last figure, pneumonia has two different causes. First one is bacteria, and second one is virus. And they look different, and the chest image of each pneumonia is different. So it's really hard to it's hard to recognize them in one pneumonia. And the other thing is the difficulty in chest X-ray itself. So in right figure, we can see some highlight there. So we know if this person has pneumonia, but without this highlight, only the experienced person can recognize if this patient has pneumonia or not. So that's kind of a difficulty of the pneumonia classification. But nowadays we are living in the era of deep learning. So there are many other previous researches which try to apply image classification models to diagnose if a patient has pneumonia or not. So the paper is published in 2017 for CheckSnet. It already outperforms the average radiologist on the diagnosed pneumonia correctly. So in this table, average level radiologist has 0.338 of F1 score, while CheckSnet has over 0.4 of F1. And these radiologists has each has 4, 7, 28, 28, 25, 28 years of experience. So I think they are quite experienced radiologists, but just quite old model which published in 2017 already outperforms. And this CheckSnet uses DenseNet, and other than DenseNet, there are so many famous neural network architecture for image classification. So in other paper, they introduce about many applications of architectures. So so in this figure, somebody uses AlexNet for like pneumonia detection, and somebody uses ResNet, and the other one has DenseNet like CheckNet, and there's another architecture called SqueezeNet. So there are many image classification architecture for pneumonia detection, and they share a common thing. The first one is all of these architectures are pre-trained on the ImageNet data. And they either do fine-tuning from end to end or just use transfer learning for the last classification layer. And the other common factor is they all use softmax layer at the end, so they can compute probability of if this patient has pneumonia or not. But softmax layer has some problem in either unseen or misclassified data. So we found a previous research called evidential deep learning to quantify classification uncertainty, which is published in 2018. And they point out softmax tends to ignore prediction confidence and tries to assign like overconfident prediction result on like some unseen data or misclassified data. So for instance, this model is trained on MNIST, like handwritten number data. And after it trained, when we put this number one image, it will says like I'm 100% sure it's one. But when we feed some other input like rotating this number one in like 180 degree, then it starts to confuse. Like if this one is rotated by 45 degrees, then it says it confuses if it's one or two, and if it's in horizontal line, then it says somehow it's number two. This model says I'm 80%, 90% sure this horizontal line is number two, but which is wrong. So this is kind of problem of softmax layer. So in this paper, they introduce new term uncertainty. So in the case if this model sees some unseen data or misclassified data or anything is strange, then it will claim high uncertainty instead of make some overconfident result and like put everything has like small probability. So this is how this paper works. So they introduce two terms. First one is belief, and the second one is uncertainty. So normally in softmax layer, so let in MNIST case, we have like +0 from +0 to +9, and if we sum all softmax result from +0 to +9, it goes to 1. But it has, but in this paper, they introduce a new term, uncertainty, and uncertainty plus some sum of or belief for each class goes to 1. So in previous one, softmax with softmax layer, it in this term only this term used without uncertainty, but they introduced a new term, uncertainty, and they also introduce a new term, evidence, and we can compute belief and uncertainty from this evidence. So belief is just simply normalized evidence. So because S is sum of the evidence plus 1, and the uncertainty is the other K. K means the number of class divided by the sum of evidence. And this evidence is just neural net output here. So here's how we can train the model with this uncertainty and belief. So in here, this alpha is, this evidence is output of Softmax layer in neural network, and we define alpha as evidence plus 1. So this is normal MSE, and in here they introduced a new loss called EDL MSE, which has this Dirichlet distribution in here. So in conceptually, it in MSE, they just directly use the result from the output layer to compute the loss. But in EDL MSE, they sample some, so they make some distribution from output of neural network and sample the result from that distribution and use that as the as probability. So that's the difference between MSE, normal MSE and EDL MSE. So after that, they can separate the uncertainty and the probability for each class, and they to sum to 1. So after this, after train this model, it will claim the high uncertainty on unseen data instead of make some random overconfident classification like this horizontal line is number 2. And so for this case, they are trained on MNIST data, and we just put some like Yoda picture. So there is no like number, the handwritten number, so it's totally unseen data. And this model says like, I don't know, like uncertainty is 1, and like every other probability goes to like almost 0. But in this EDL has also a problem where the sample is like in between like 2 classes. So in case 1, like let's say there are two classes, and in case 1, the evidence of number 1 is 0.8 and evidence of number 2 is 0.0. It means it's like quite clear this case 1 belongs to class number 1, and it says uncertainty, and we can compute some uncertainty value from here. But in case 2, if like this sample looks like half number 1 and half number 2, then the model will return like some like 0.4 and 0.4 value. And in this case, it's quite uncertain because we don't know this class belongs to 1 or 2 exactly. But in EDL form, the case 2 returns uncertainty as the same value as case number 1. So it's so in this case, case 2 is as uncertain as case 1, but in our case, we don't we think like case number 2 is more uncertain than case number 1, and okay, and it's more critical for our cases because in MNIST data, as you can see, all classes are pretty like different. So like let's say like number 8 and number 3 are similar, but any other classes looks very different. But in our cases, so the left example is pneumonia and right example is healthy person, and it's really hard to recognize like where is different and like, what is different here. So in our case, most of because we use just X-ray data, so most of frames like human body looks same, and there's only a few difference between in like this lung area. So it's easily it's really hard for model. It's easily to confuse like if this data belongs to pneumonia or not. So we suggest a new new strategy to compute uncertainty by using quadratic form of evidence. So in here, we use in EDL, evidence is just EK, so output of neural network itself, and we will use the quadratic form of this evidence. So like the other following equations goes to like this, and since it still satisfies this constraint u plus like sum of beliefs are equal to 1. But in the case of in the previous case, like case 1 has like belongs to 1, in case 2 sample for case 2 like is confusing if it's 1 or 2. In EDL, uncertainty of this value are same. Case 1, case 2 are same, and the predicted probability are, yeah. So in here, number 1 is higher, and in case 2 they are 50-50. But in our case, we also return similar result of predicted probability. It's like slightly smaller confident probability in case 1 and exactly same as case 2. But in uncertainty, we will report higher uncertainty in case 2 because in this case, model has no idea if this sample belongs to class 1 or class 2, which is uncertain. So this is our proposed method. And next time I move to experimental result. So first I'm gonna introduce the data set. We use NIH chest X-ray, which has more than 100K chest X-ray images from 30,000 unique patients with 14 diseases. But we only pick the pneumonia and normal case for the binary classification. And we use data augmentation. We use horizontal flip for data augmentation because other methods such as vertical flip doesn't make any sense for the chest X-ray. So we just only use horizontal flip. And this is how we divide our our data set into train, test, train, validation, and test. So we, because in this data set, there are so many normal chest X-ray compared to the pneumonia. So if we train it with like, we simply divide it like half for training and half for test, then in train set, there must be like superior number of normal chest X-ray data compared to pneumonia. So we think our model will return all for normal to make a good loss. So we make a balance for the trained data set, but for validation and test we don't have to. So we just put like sampled it randomly. So this is experimental result. So we compare the baseline, which is CheckSnap, and the second one is EDL, and third one is ours. So as you can, network are same. So this one is DenseNet, and we will use DenseNet 121. And the baseline uses binary cross entropy loss, and while EDL and ours are using EDL MSE with these evidence values. So in terms of AURC, the baseline has the best score, but the others are similar. But the difference between baseline and EDL or ours are not that significant. But in terms of accuracy, we have like 80% of accuracy, while this CheckSnap baseline has 70% of accuracy.
제가 지금 이동 중이라서 그 채팅에다가 좀 물어볼게요. 그 방금 이 슬라이드에 대해서요.
네.
네, 동일한 거 썼습니다. 네.
네. 그러니까 트레인셋에서 1대1로 맞췄지만 나머지는 그냥 랜덤하게 맞춘 게 이스라엘 EDL 아웃 다 똑같다는 말씀이군요.
네, 네.
아, 예, 알겠습니다. 네, 진행해주세요.
Yep. And the next result, we compare the correlation between difference in belief and uncertainty. So, which means, let's say there are only two classes, and belief one, if like belief one and belief two are different, that means that means model is quite sure if this sample belongs to class one or class two. But if like difference between belief is small, it means model is confused. Like the sample is confusing and model has no idea if the sample goes to one or two. So in our assumption, that case is uncertain. So we are going to, we compared the correlation between belief difference and uncertainty. So in EDL, there is no correlation between belief difference and uncertainty. So EDL doesn't matter if the belief values of each class are different or not. They only concerns the sample is unseen or misclassified. But in ours, if difference between beliefs gets smaller, then uncertainty grows. So that's why we have like negative 0.5 correlation in here. And these are some diagrams to compare this correlation. And these are the final result of these are final result for this when Yoda image comes to the model trained on MNIST data. So this is previous example for EDL, and this is our model. So our model has slightly higher result for number 2 in here, but anyway, it's pretty small, so it's less than 0.2, and we have like high uncertainty like 0.95. So this highest value might be problem, but because we have high uncertainty, I think it doesn't really matter if to put this Yoda as unclassified. So this is our conclusion and future works. So we proposed 2 new ideas. So first, because a softmax layer has some problem in like confusing or misclassified or any of uncertain values, uncertain samples. So we applied a concept of uncertainty in this pneumonia detection task, and we also redefined the uncertainty to consider the confusion. Confusion means a sample is like the model has no idea if the sample belongs to class 1 or class 2, and confusion to fit the chest X-ray data. So as a result, our model has the better accuracy than like other baselines or previous evidence model with the similar AURC value. And our future work, as we researched on our data set, these labels on the image chest X-ray data is extracted by NLP model, so which can be some errors, which can contain some errors. So probably there are many a few inaccurate labels in this data. So probably we can improve by fixing this. The other one is because like our work team members has no background of medical we are no doctors and we have no medical background, so probably medical feedback will be helpful to analyze our examples and design the model. And these are our references, and this is the end of my presentation. If you have any question, feel free to ask.
네, 채팅에다가 남겼습니다.
기본적으로 플립 같은 거를 사용하는 거는요. 그게 굳이 꼭 현실성이 없을지라도 어떻게 보면은 다른 그냥 위치를 암기해서 얘가 어떤 결과를 내는 거를 막기 위해서라도 네, 그거는 사용을 하는 게 좋은 것 같고요. 그리고 그 말씀하신 이 리졸트가 다른 요소 때문에 올라간 것인지 그러니까 uncertainty를 잘 모델링해서 올라간 것인지는 저희가 생각하기에는 저희가 그 experimental result 두 번째 페이지에 그 왼쪽 아래에 표를 그려놓은 게요. 네, 이걸 보시면은 저희가 이제 랜덤 인풋을 넣었을 때의 불확실성이 확실히 다르게 다르게 값을 갖는 게 나타났고, 그래서 이거 외에는 다른 영향을 줄 수 있는 요소들이 없었기 때문에 저희는 요게 영향을 줘서 성능이 올라간 거라고 네, 그렇게 결론을 내렸었습니다.
네, 말씀하신 대로 저 정도면 충분히 잘 하신 것 같고요. 굉장히 의미가 있는 연구 같습니다. 논문으로 계속 이어질 수 있도록 한번 잘 해보시면 좋을 것 같고요. 네, 4번 팀 이제 준비되셨으면 바로 이어서 해주세요.
Hi, can everybody see the screen?
네.
Okay. Good morning, guys. I'm Eunyo with teammates Kwon-Ho-yeon, Kim Hae-rim, and Lee Young-ho, and I'll start my presentation on septic shock and mortality prediction of sepsis patients. Sepsis, which is 폐혈증 in Korean, is a life-threatening condition that arises when the body's response to an infection causes injury to the tissues and the organs. It is an inflammatory immune response triggered by infections such as bacterial infections, fungal infections, or viral infections. And sepsis is one of the most common death causes in Korea, ranked at 11th with 9.1 deaths per 100,000 people in 2018. And recently, it was published in The Lancet, which is one of the most prestigious medical journals, that sepsis is now the global leading death cause, being ranked over cancer. Such prevalence and severity of sepsis makes sepsis one of the most extensively studied diseases. The diagnosis of sepsis is done through measuring inflammatory features as shown in the table by measuring temperature, heart rate, respiratory rate, and white blood cell count. And the treatment is done through antibiotics and maintaining body functions so that the body can fight off the infectant. Sepsis shows symptoms similar to the common cold at first, such as fever, but the deadly part about sepsis is that it may lead to septic shocks, which increases the mortality rate of the patients to 80%. Although sepsis is treatable through identifying the cause of the infection and treating it, because mortality rate increases so rapidly once the patient develops septic shock prediction is important in the treatment of sepsis patients. So we propose a new model for this conventional task of predicting septic shock development in sepsis patients. In specific, we developed an interpretable multitask model through a simple extension of Retain for simultaneous prediction of both septic shock and mortality in sepsis patients. We hypothesized that because septic shock and mortality are two closely related tasks, learning both tasks would allow the model to learn information useful in predicting septic shock when learning to predict mortality. One of the recent works in sepsis prediction is the work by Lee et al., which aimed to discover septic shock pre-shock state that can be used to easily identify septic shock development. They hypothesized that because patients show fluctuating vital signs before they experience the shock itself, as highlighted in yellow in the figure, accurate prediction of this novel pre-shock state would lead to quicker treatment for sepsis patients. They use several conventional machine learning models, such as generalized linear models, XGBoost, and RNN, and the conventional baseline model in the medical domain, the Cox proportional hazards model, to predict septic shock and discover and describe the physical state the septic shock patients show before developing the actual shock. Another work in relation to sepsis prediction is the work by Harit Yunyan et al., which proposed a simple multitask LSTM architecture for multitask prediction. In their work, their main task was predicting decompensation, which quantifies the risk the patient is experiencing by summarizing fatal diagnoses, including septic shock. In predicting this decompensation, they added 3 auxiliary tasks. While predicting decompensation at every time step, they predicted the remaining length of stay per every time step as well, and they predicted mortality and phenotype label once during the training sequence. The model was trained to minimize loss created through a weighted sum of all 4 tasks. And in their case, the multitask model showed better performance than the single task models in mortality prediction only and not in the other 3 tasks. Another multitask RNN architecture for predicting medical events was proposed by Yu et al., where they added a reconstruction task as the auxiliary task in predicting in-hospital mortality. Although they added attention mechanisms for both tasks given to the model, the main usage of the attentions were so that the model would learn from all time steps appropriately. Hence, they only learned attention for the time steps and not for each input feature they included. And lastly, because our model is based on Retain, we included a short recap of Retain that we all learned in class. Retain learns two RNNs from the input embedding, where one network learns the visit level attention and the other learns the item level attention. These attentions are then combined with the embedding vector to create a context vector, which is used for the final prediction. Because Retain provides interpretability regarding both time level and item level input, we use this model as our building block for our multitask model. To train the septic shock prediction model, we extracted patients diagnosed with sepsis in the Mimic3 database. We use ICD-9 codes as our diagnosis standard. And septic shock labels were also extracted using the septic shock ICD-9 code. We extracted the mortality labels for each hospital admission to use as our auxiliary task. For the features, we use the feature set available in the chart events table as listed in the work of Lee et al. And this included various items measured from the patients, including heart rate, respiratory rate, temperature, and white blood cell count, which are the basics for sepsis diagnosis. And the feature set included other important measurements such as creatinine as well. As the sequential medical works do, we used a sequence of events for the first 12 hours of each hospital admission to predict septic shock development. We limited the maximum time step to 100. And in each time step, we created a feature vector where each dimension was an item ID, and the measurement values for the respective item ID were used. Before explaining our model, I would like to first go over what multitask learning is. As the name tells, multitask learning is where we train a single model to handle multiple tasks. Conventionally, this is done by learning a shared representation through shared layers and taking this shared representation and passing it down task-specific layers for each prediction or regression task. This allows the model to learn information across various tasks, resulting in a more generalizable model. Multitask learning also allows the model to learn information that is useful for a task, but difficult to learn in typical situations. For example, there may be information that is useful in predicting task A, but not easily learned by the model when trying to predict A. This information then could be potentially be easily learned when trained on task B, when A and B are related or correlated. Then training the model simultaneously on A and B would help predict both. This is our proposed multitask model for predicting both septic shock and mortality, in which we named it Multitask Retain. It is a simple extension of the original Retain model where the embedding layer is shared across both tasks and task-specific Retain modules were trained. As was in the original paper, the embedding layers, which can be linear for interpretability or MLP if necessary, is used for both the septic shock prediction task and mortality prediction task. Hence, this embedding is used as the input for all 4 RNNs that we trained. Then a retain module for each task is trained using this embedding. A RNN for time level attention and a RNN for item level attention are trained for each task, and the prediction for each task is made using the shared embedding and the attention from the respective pair of RNNs. The characteristics of each layer follow from the original Retain paper, except that we used a bidirectional RNN for all of the RNNs. Hence, alpha and phi would be the time level attention vectors, and beta and psi would be the item level attention matrices, which show the attention for each item at each time step for each task. The embedding V is learned by jointly optimizing both prediction tasks, where we take the average of the losses of the 2 tasks as our objective. In our multitask model, the interpretability, where we can calculate the contribution of each input to the final prediction, can be made in the exact same manner in the original paper because only the embedding layer is shared and separate retain modules are trained per task. Therefore, it will be possible to compare the contribution of the same input in predicting each individual task. We compare the performance of on AURC and AUPRC of MT Retain to several baseline models. We included logistic regression, SVMs, and GBMs as the non-neural net baseline models, and GRU and single task retain with bidirectional RNNs as the baseline deep models. While the non-neural models and GRU had poor performance for both septic shock prediction and mortality prediction, Retain and MT Retain had a significantly higher performance. MT Retain, whether the embedding layer was linear or nonlinear, had higher performance than when Retain was trained on each task separately. The linear embedding version of MT Retain had the highest performance for mortality prediction with AURC of 0.850 and AUPRC of 0.880, and the MLP embedding version of MT Retain had the highest performance for septic shock prediction with AURC of 0.827 and AUPRC of 0.722. So through the results, we can assume that MT Retain is able to learn an embedding that can predict both tasks well, and that using the attentions generated from the shared embedding was effective in predicting septic shock. The fact that MT Retain performed better than single task retains show that septic shock and mortality are two tasks that contain information in predicting the other, which was expected as the two tasks are logically closely related. So in conclusion, we proposed a multitask extension of Retain, which outperformed all baseline models. From this, we could see that learning septic shock and mortality simultaneously actually improves the predictive ability of the model regarding both tasks. MT Retain can be easily extended to more tasks since all it takes is to add a retain module on the shared embedding layer per added task. And also recently there have been multiple multitask papers that consider multiple modalities where the input embedding is created by combining data from different data sources. MT Retain may be also easily extended to such modal situations where data typically used for certain tasks may be used together with the original input to provide information to the model for tasks that would not normally use such data. While we trained the model on two closely related tasks and saw improvement in predictive performance, we could also test MT Retain on seemingly unrelated tasks to see how generalizable the model is. Thank you, and if you have any questions, feel free to ask.
잘 들었습니다. 혹시 그 인터프리터블 데몬스트레이션 같은 건 따로 없나요?
Interpretability demonstration이야?
네네, 뭐 그 컨트리뷰션 계산한 거라든가 뭐 이런 퀄리테이티브 이밸류에이션 슬라이드 같은 거 하나 따로 없나요?
네, 그 저희가 그거를 시도를 했었는데 그 안타깝게도 계속 그 계산이 잘못되고 그 제 커널이 죽어가지고 저희가 결과를 내진 못하고 실지 못했습니다.
네, 리테이닝 그 장점이 이제 그 말씀하신 그 인터프리터빌리티인데 이거를 멀티태스크 하셨다는 거가 좀 참신한 것 같아가지고 궁금했는데 그러니까 사실 리테인 하나만으로도 소프트맥스, 그러니까 지금 이게 스태틱 쇼크, 멀티리티가 다 바이너리 태스크잖아요. 근데 그거 아예 리테인의 그 프리딕션 레이어 소프트맥스를 달아버리면 그거 자체도 약간 멀티태스크처럼 아니구나. 이 두 개가 완전히 다른 태스크구나. 네, 하여튼 창실하실 것 같아요, 제가 보기에는. 그래서 이건 그 인터프리터빌리티도 보장이 되는지 되게 궁금했거든요. 아쉽네요.
네네.
그리고 그 익스페리먼트 쪽에서 이제
예.
리테인이 다른 모델들보다 훨씬 잘하는 것 같은데, 그게 혹시 다른 모델들의 파라미터 수가 어느 정도 비슷한가요?
예, 죄송합니다. 제가 잘 안 들려가지고 다시 말씀해 주실 수 있으세요?
저 채팅에다 물어볼게요.
예. 네. 그 실험 그 파라미터, 하이퍼 파라미터 같은 경우는 리테인 학습시킬 때랑 MT 리테인 학습시킬 때랑 다 동일하게 가져갔습니다. 네네. GRU 같은 경우도 동일하게 이제 가져갔고, 이제 넌 뉴럴 모델들 같은 경우는 그냥 따로 이제 최적화해서 학습했습니다. 바닐라 GRU는 바이디렉셔널 하지 않았던 것 같은데, 저희 그 팀원분 확인해 주실 수 있나요? 이 부분에 대해선?
네, 알겠어요. 그렇군요. 왜 여쭤봤냐면은, 리테인이 사실 GRU보다 그렇게 잘하기가 쉽지가 않거든요. 오히려 못할 확률이 더 높기 때문에, 왜냐면 인터프리터빌리티를 강요하기 위해서 리니어한 스트럭처를 가져가기 때문에 그런 제약이 없는 GRU보다 탁월하게 잘하는 경우가 거의 없다고 보시면 되거든요. 네, 전반적으로 굉장히 좀 리테인을 멀티태스크 한다는 거가 조금 참신한 것 같은데, 그리고 저희가 죄송합니다. 제가 지금 버스를 타고 있어가지고. 네. 근데 저희가 그 수업에서 배운 거에 굉장히 그 익스텐션을 잘 하신 것 같아서 아주 좋은 것 같습니다. 혹시 이거 워크샵이나 이런 데다 내실 생각이 있으신 건가요?
저희 팀원들끼리 얘기를 해봐야 되는데, 아직 그런 그 계획을 저희끼리 얘기를 하진 않았습니다.
혹시 뭐 그러실 마음 있으시면 또 저랑 따로 나중에 얘기를 해보시죠.
예, 알겠습니다.
네, 그럼 발표 잘 들었습니다. 감사합니다.
네, 감사합니다.
Okay, I'm sorry I spoke in Korean, actually. That was a mistake. So, all right, thank you everybody for participating in the final project presentation. And I think this is officially the end of the entire course for this semester for machine learning for healthcare. I hope everybody had a I hope everybody learned something at least, or had like a pleasant learning experience overall. And if you guys have any feedback, please leave any message in class somewhere. You can send emails to myself or the TAs. All right, if there are no more comments, we'll end the class now. And thank you very much. I'll stick around maybe a couple minutes in case there are any questions. All right, thank you guys. Bye-bye.